Okay, let's start. So in this video we are going to discuss some topic of chapter number 3, that is about transport layer, in the book Computer Networking, a Top-Down Approach, 8th edition. So in this 8th edition book, which is published in 2020, in this book there are some advanced topics, new topics. So there are some additional topics that are not covered in the 7th edition. So we are going to discuss those topics. So as we know that the TCP, they have different versions, different flavors, and we have discussed for example TCP Tayo, TCP Reno, and there are many other versions that are used and practiced. So we are going to discuss another version of the TCP, that is called TCP QUIC. Okay, so let's discuss what is TCP QUIC. Okay, the TCP QUIC, basically if there are some problems in the TCP Tayo and Reno. In this TCP Reno there are some problems, and what are these problems? So for example, the problem is that if we have long distance network, so those TCP Reno, it cannot perform well. Okay, so for this purpose the QUIC protocol was suggested. Okay, so first let's discuss that what could be the problem if there is a long distance network. Okay, so what could be the problem of TCP Reno if we have long distance networks? Okay, so suppose we are going to explain it through an example. Suppose at time 0, and this is the 10 a.m. suppose the sender and receiver, they are exchanging the data using the TCP Reno. Okay, and suppose at this time 10 o'clock the congestion window is equal to 2. Okay, and we have to exponentially increase the congestion window. Okay, so as we know that after receiving an acknowledgement after 1 RTT, okay, the congestion window is increased exponentially if it is in the slow start, but if it is in the congestion window, congestion awareness, then it is increased linearly. Okay, so suppose that we are increasing exponentially, and we are in the slow start. Okay, so suppose if the congestion window is 10 and the RTT is congestion window is 2 and RTT is 10, and if the RTT is 5, then what are their effects? So we know that the congestion window is increased exponentially after receiving acknowledgement. Okay, when acknowledgement is received, after 1 RTT. So if the RTT value is equal to 10 seconds, okay, so after 20 seconds, what should be the value of congestion window? Okay, so if you say the RTT is equal to 10, so it means that after 10 seconds we will get the acknowledgement. When we get the acknowledgement, we will increase the congestion window exponentially. So after 10 seconds we will get an acknowledgement, so we will increase congestion window exponentially, so it will be increased to 4. So after 20 seconds, after next 10 seconds, after total 20 seconds, another acknowledgement will be arrived and the congestion window will be increased from 4 to 8. Okay, so if the RTT is equal to 10, then after 20 seconds the congestion window in this case it will become 8. Why? Because after 10 seconds we will get an acknowledgement and the congestion window will be increased exponentially. It will become 4. After next 10 seconds, after next 10 seconds means after 20 seconds we will, so after 20 seconds if the RTT is equal to 10, so we will receive 2 acknowledgement, and we increase that when we receive the 2 acknowledgement, so we will increase the congestion window by up to 8. Okay, for the first RTT it will be increased to 4, and in the next RTT it will be increased to 8. Okay, if the RTT is equal to 5, So what will be the congestion window after 20 seconds? So if the RTT is equal to 5, so we will receive 4 acknowledgement during these 20 seconds. So the congestion window will be increased 4 times. So for the first time, the congestion window will increase from 2 to 4, next time from 4 to 8, next time from 8 to 16, and next time from 8 to 16 to 32. Okay, so you can see that, if the RTT is equal to 10 seconds, then after 20 seconds the congestion window will become 8. If the RTT is equal to 5 seconds, the congestion window will, after 20 seconds it will be is equal to 32. So you can see that if there is a long distance network, where RTT is greater, then it will take longer time to reach to maximum threshold value, that is SS threshold, the congestion level, the maximum capacity of the network. Okay, and if there is a short distance network, that is RTT is smaller, then the congestion window will increase exponentially more faster, and it will reach to the network capacity level early. Okay, so this is the problem in TCP Reno. So how to solve this problem? So the TCP Reno, the TCP Tayo, they work based on RTT. When the acknowledgement arrives, then they increase the congestion window. So the congestion window is increased depending upon the receiving acknowledgement. Okay, so this is the problem, and there are some other problem as well. Okay, so and for those problem you can access these links. Okay, and you can also consult, you can also read from the book also. So in the 8th edition this topic is covered, and some links are provided where you can find the additional information. Okay, so this problem is solved by QUIC, the TCP QUIC version. So let's discuss how the TCP QUIC version works. Okay, so first of all, the TCP QUIC version, it is basically installed as a default in the Linux version. Okay, and the TCP, it differs from the TCP Reno only in the congestion control algorithm on the sender side. The rest of the working, it is same as compared to TCP Reno. Okay, for example, the QUIC maintains the acknowledgement clocking, that is the congestion window increases on the receipt of acknowledgement. When the acknowledgement is arrived, then the congestion window is increased. But how the congestion window is increased, this is different in the QUIC than the TCP Reno. Okay, and similarly there is no change in the TCP QUIC regarding the fast recovery and retransmit mechanism. So the fast recovery and retransmit mechanism, they are same in the QUIC and in the TCP Reno. Okay, so the only difference in the QUIC algorithm is that it uses a QUIC function rather than a linear window to increase the function of current TCP standard, to improve the scalability and stability under fast and long distance network, as I have explained. That is, QUIC is basically is designed for the long distance network. Okay, so let's discuss how the TCP QUIC works. Okay, so whenever there is a congestion happens, what does it mean? Congestion happens means that suppose at this point the network congestion happens. So how it is detected that the congestion happens? Due to duplicate acknowledgement or packet loss. Okay, whatsoever is the case. Okay, duplicate acknowledgement. So what should we do? So first of all, this point is noted. This is called WMAX. This is called WMAX. This is the state where the last congestion happens. Okay, so this state, this value, the congestion window, it is called WMAX. It is noted. Okay, so again, after noting it, the congestion state, what we do, first of all, we have to half. So there are different, actually this, when congestion happens at this point, okay, so this value is noted. This is called WMAX. And now the new congestion window, it will be decided based on this function. WMAX is multiplied with the beta, and beta is a constant. Okay, beta is a constant. Okay, and what is its value? Its detail is available in the TCP QUIC RFC. Okay, so based on this formula, the new congestion value is decided. For example, if it is beta is equal to 0.5, so okay, so and W max is equal to 20, suppose. So what should be the new value of the congestion window? So 20 multiplied by 0.5, it becomes 10. So the new value will be half 10. So it will start from here. Okay, so this is the first step, that when the congestion happens, the congestion is detected, so the packet loss is detected, so the congestion that value is recorded as W max. And second is we compute the new value of congestion window. So the new value of congestion window is computed based on this formula. Okay, after this, when the data is transmitted, so how the congestion window should be increased? So the congestion window is increased based on this formula. The congestion value is increased based on this formula. So what are these? C is a constant. It is a fixed constant. Okay, and it shows how aggressively the congestion window should be increased. Okay, typically its value is 0.4. Okay, so these detail you can find in the RFC as well. This T, what is T? T is the elapsed time from the beginning of the current congestion window. For example, when this congestion happens, okay, so it was 10 o'clock. It was 10 o'clock. This time was 10 o'clock, 10 a.m. And now when the new packet are transmitted, for example, it is 10:30. So 30 seconds has been passed. 30 seconds has passed. Okay, so this is the difference of QUIC from the TCP Areno, that the number of the size of congestion window, it depends on the time. It depends on the time. The time that is elapsed from when you are sending the new data, this is the time, and this time is and this time is this is the time when you are sending the data. So what should be the congestion window? The congestion window size, the increase in the congestion window, it depends on the time elapsed from this time to this time when the congestion was happened. So the difference between this time, this is called T. Okay, so if you receive one RTT after 30 seconds, okay, so the congestion window size, it will increase depending upon the time. If there is 30-second time, so it will increase according to 30-second time. If you received the RTT in the 10-second, so its congestion window will be different. Okay, so this is the difference. Okay, the second is T is the time elapsed from the beginning of the current congestion awareness, and K is the time that above function takes to increase the current window size. Okay, so how quickly you should reach from this value to this value, how quickly you should reach, so this depend on the K. Okay, and what should be the K? So the K formula is this one. Okay, here the what is cubic root? This is basically the cubic root function. This is exponent. Okay, so this W max, again it is the value of the congestion window when the last congestion happens at maximum value. Okay, and beta is what? It is a constant that is used to decide when the congestion window happens. So the new congestion window should be what? So it should be depending upon this beta value. Okay, and C is a constant. Okay, so this value, this function value is after computing the K value, it is put here, and now the next congestion window size is defined, and then that according to that value the data is sent. Okay, so this is the difference. Okay, so you mean that basically the TCP QUIC function, it takes a concave approach. Why? Because the more you take the time from the last congestion window, it will take longer time. The congestion window will increase greater. But as you reach to the congestion status, so it will become, so the congestion window increase rate, it will be decreased. Okay, so at the when you are far away from the congestion state, for example you are here, so the congestion window will increase with the higher rate. But if you are getting closer to the congestion state, then the rate of increase in the congestion window, it will be decreased. Okay, so it takes this value. Okay, so this is the difference, and you can see that the TCP Reno, it is a linear. Okay, so K itself, the value K is itself it is a tunable. Okay, it is adjustable. Okay, so you can see that we increase the congestion window W as a function of the cube of the distance between current time and K. So this is the difference, that the QUIC use this function to increase the congestion window size. Okay, so it perform multiplicative decrease of congestion window by a factor. When the congestion happens, so the congestion window is decreased by a factor W, not half. So it is adjustable. In the TCP Reno, when the congestion happens, so the congestion window size is when the packet class is detected by 3 duplicate acknowledgement, so it means congestion happens, so the congestion window is decreased by half. But in the QUIC, it is not half, it is a generic. It is reduced by beta, and what is the beta value? You can set it. Okay, after this it start increase the congestion window depending upon the equation number 1. Okay, so this has a concave growth continues until the congestion window reach to maximum saturation value. Okay, when it reaches to maximum, so as the congestion window approaches this maximum capacity value, so the rate of congestion window decreases. So the congestion window is increased slowly. Okay, so you can see that when the congestion window reaches to maximum value, so it is closer to this saturation window, so again it will increase slowly. But as it gets higher, it gets for example, when the congestion was detected and it was, for example, at 20, but actually the network capacity is 40. Okay, so after 20 it will increase slowly, but as it moves from this point away, again it will the rate will be increased, the congestion window size, it will be increased. Okay, so here it is a concave and here it is a convex time. Okay, so this is again a difference. In the TCP Reno, it will increase linearly. Okay, up to this point. Again after this it will be smooth, but here in the TCP QUIC it can increase also from that point where the congestion has happened. Okay, so convex window growth begins larger increase when the congestion window gets away from the this size. Okay, so there is a smaller increase, as the congestion window gets closer to this point, so there is smaller growth in the congestion window, and when it crosses, then again it is a smaller increase. Okay, but as it gets far away, then the size of the congestion window increase faster, it increase more. Okay, so basically the TCP QUIC, it is a QUIC. This protocol is by default used in the Linux, and nowadays it is also used by popular web servers. Okay, so because of this advantage. Another important problem that we have, these are the mechanisms that we are going to discuss that are used for congestion avoidance. Okay, we have, for example, what happens when the TCP they transmit data, so physically it pass through routers. Okay, so in these routers, if they get congested, so the packet are lost. If there are more packets in the queue, then the incoming packet will experience more delay. Okay, it will have more delay. So even if the bottleneck link, they always become busy and they always get full. When they're full and more packet arrive, then those packet will be lost, so the congestion will happen in the TCP. So what should we do? Usually when we increase the TCP sending rate, it will not increase end-to-end throughput. What is throughput? The number of packets that are received in a particular time. For example, if 5 packets are received in 10 seconds, and in another scenario 20 packets are received in 10 seconds, so the throughput is increased when the 20 packets are received in 10 seconds. Okay, so when the TCP sending rate is increased, so it may not increase the throughput. Why? Because if that packet pass through a link and the buffer is full, that packet will lose. So that packet will not reach to destination. If that packet is not reached to destination, then the throughput is decreased. Okay. Similarly, if the buffer is not full, the packet is not locked, but the buffer has many packets in the queue, so that packet will wait. And will that packet wait? So there its acknowledgement alive late. So the RTT will increase. When the RTT increases, so the throughput will increase. Okay. So what should we do? Always the purpose of the internet is to keep the end-to-end pipe full but not fuller, because if it is fuller, then the arriving packet will experience more delay, so throughput will decrease, and if the queue is full, then the packet will be lost. Okay, so we have another mechanism that is called delay based TCP congestion mechanism. Okay, and this is used in this purpose. How it works? In the delay based approach, when the packets are exchanged between sender and receiver, okay, so the sender, when it receives the acknowledgement, so it computes the RTT for each acknowledged packet. So suppose the sender has transmitted 100 packets, so the sender has noted the RTT for 100 packets. So which RTT is minimum? So the minimum RTT of the 100 packet is noted. This is called RTT minimum, and this is called minimum observed RTT, and this is called because it is minimum, so it means that at that time the path is not congested. So for this minimum RTT, the uncongested throughput is computed. Okay, and what is the throughput? The throughput is the byte sent in interval divided by that interval. For example, this RTT is 5 seconds. Okay, and the packet that are sent, the bytes that are sent in that RTT, for example, it is 100. Okay, so 100 by 5, so 20. So 20 is the throughput. Okay. So similarly, first of all, this RTT minimum is noted. For example, if we have transmitted 100 packets, and we have the sender has received the acknowledgement for 100 packets, so for each packet the RTT will be computed. So for these 100 packets, which packet has minimum RTT, that becomes the RTT minimum. Okay, so for that RTT minimum, the congestion window, the throughput is computed, and the congestion window divided by RTT minimum, it is divided, and this is become uncongested throughput. This is called uncongested throughput. Okay, so after computing this uncongested throughput, so if the measured throughput, for example, if the sender is sending more data, okay, so the sender will compute the RTT and the throughput. So if that throughput is very close to this uncongested throughput, then the congestion window is increased linearly. For example, if we have sent 1 packet, then we will send 1 packet more. If we have sent 2 packets, then we will send 1 more packet, 3 packets. Okay, so otherwise the congestion window is decreased linearly. Okay, so this is the working of delay based TCP congestion control. Okay, so the delay based congestion control, it basically works without enforcing the packet loss, without inducing packet loss. It takes the action, prior actions to go to avoid the congestion control. So it is used to avoid the congestion control. Okay, and it is also deployed by a number of approaches. Okay, for example, BBR it deployed on Google internal backbone networks, so they are using delay based TCP congestion control. Okay, okay, so next, okay, as we know that internet transport protocol, we have discussed two types of protocol. One is called TCP and one is called UDP. The TCP, it has features reliability, flow control, congestion control, okay, and connection oriented. The UDP, it doesn't have anything, no reliability, no flow control, no congestion control, and no connection oriented. Okay, suppose we have an application, and that application, it only needs a reliable transport service. It only needs this transport reliability, no flow control, no congestion control, no connection oriented. What should it do? It should use TCP or you should use UDP. If UDP is used, then there is no reliability. If the TCP is used, there is reliability, but there are other things: flow control, congestion control, and connection oriented. And this application doesn't want these things. So what it should do? So the answer is that, so neither we can use TCP nor we can use UDP. So what should we do? We should use the application layer, okay, on the UDP, and the reliability should be implemented at the application layer. Only reliability should be implemented at the application layer. Okay. So another way of this is that nowadays we have a QUIC. This is a protocol. This is a QUIC protocol over UDP internet connection. Okay, so we discuss how this QUIC works. Okay, it is basically now it will be standardized, and it will be also used in the Windows and other operating system and application. Okay, so another things. So as we know that we have different flavors. We have two protocols at transport layer, TCP and UDP. And there are different versions of TCP. And for example, we have discussed TCP Tayo, TCP Reno, TCP QUIC, TCP QUIC, and the TCP QUIC. Okay, and delayed congestion protocol. Okay, so and these are used for different purposes, different scenarios, different applications. Okay, so nowadays we have another protocol which is called QUIC. And this QUIC protocol, what is it and how it works? So basically it is an application layer protocol on the top of UDP. Okay, and how it works, let's discuss it at some features. So first of all, QUIC is an application layer protocol over UDP. The QUIC means QUIC UDP, U for UDP. So Q is for QUIC, UDP, internet connections. So it is an application layer protocol. It is used on the top of UDP. It increases the performance of HTTP, and it is deployed on many Google servers and application, for example Chrome, mobile, YouTube app, etc. Okay, so how the HTTP 2 point works? So HTTP 2 point works. So HTTP is an application layer protocol. If we need security, we have to implement TLS as a security layer protocol. Then we have to implement TCP, a transport layer, okay, and so on. But in HTTP 3, we combine the HTTP 2 and QUIC together over the UDP. So this is the difference of HTTP 3. And what are its advantages? We will discuss them. Okay, so this is the architecture difference, that we run the HTTP over UDP and HTTP 3. Why? Because the HTTP 2 is implemented the application layer along with the QUIC, and the transport layer we implement the UDP. Okay, so how it works, let's see it. So the QUIC protocol, it adopts approaches that we have studied in this chapter for connection establishment, error control, congestion control. So all these things are adopted. Okay, for how they are adopted, so you can have the quick RFC or specification, and you can know about it. Okay, it have connection establishment mechanism. Along with the connection establishment mechanism, one of the difference of the QUIC protocol from the TCP is that it also have authentication and encryption embedded. But in the HTTP 2.0, we have for security we use another application layer protocol which is called TLS. Okay, but here the security is embedded here. Okay, so what is its advantage? We will discuss it. So another advantage is that there are multiple application level stream that can be multiplexed over single QUIC connection, and this is the advantage of HTTP 0.3, and we have already discussed it. Okay, so basically the existing separate reliable data transfer from security. So let's see it. For example, if you are using HTTP 2.0, so first of all the TCP connection will be established by using the TCP protocol. So one RTT is required for TCP connection establishment, and then if you are using TLS for security, so we need one RTT for security establishment or handshaking in the TLS. So after 2 RTT, then you can send the data. But in the QUIC protocol, it is much easier, because in the QUIC handshake, in one handshake, not only the connection is established, but also the authentication and these things are performed. So it is much faster. Okay, so QUIC protocol requires one handshake, but in the TCP protocol it requires 2 handshaking, for one for TCP connection and another is for the TLS for security. Okay, so this is another advantage of QUIC HTTP 3.0 or HTTP 2.0. Okay, let's discuss the streaming mechanism, how it works. So we have already discussed it, because it doesn't have as you know that in the HTTP 1.0 what we have, for example, we have HTTP application layer protocol. At the transport layer we use TLS, and we use TCP reliability or congestion control here at the transport layer. But in the QUIC protocol we use application HTTP and QUIC protocol, and then we use these things are implemented at the application layer, and at the transport layer we use UDP. Okay, so let's see it. For example, if when we send 3 data, okay, and one data is received correctly, the another one is lost at the transport layer, then it will be you can see that the second one, it was lost. The first one is received, the second one is lost at the transport layer. When it is lost, so it will be sent again. You can see that it is sent again. Okay, and the third one is sent. Okay, so this is the difference. So until the first one is sent, until the second one is not received, the third one cannot be transmitted. But here it is different. You can look it here. When the second one is lost, so the third one cannot be transmitted until the second one is correctly received. But here each data stream is packet, they are treated independently. Okay, so here if the first packet is received, okay, if the second packet is lost, so the third packet can be transmitted at the same time, because it will not wait, because this is another stream. If it is another stream, so this stream is independent from this stream. Okay, so this is the advantage, that there will be no head of line blocking. Okay, so for more detail, please study these topics in the books. In this 8th edition book, these topics are covered in detail. Okay, and some links are given where you can find the additional information as well. Okay, thank you. By this we end this video. Okay.